Right, everyone. We are back here today at a new lesson, and we're going to be focusing on the Grey Wolf optimization method. And that method was inspired by the Grey Wolf natural behavior that they use when they are hunting other preys. This method was also taken from and inspired by Syed Ali Mirjalili, as he have mentioned that and invented this method that would be an alternative to other optimization methods that include ant colony, swarm particle optimization, etc. etc. So the good thing about this method is that it is a mix of both exploration and exploitation. There is a balance between them both that makes it good for practical use. It is inspired by the way the wolves are hunting in real world because um, the wolves are just encircling their prey, and after they find it, they're encircling it, and then they're hunting it, and then they're attacking the prey. And this is how we're gonna move to find our prey. And when we say a prey, we are referring to the final answer, our aim, goal to reach that answer for our iteration to converge. So, I have done an explanation in the last lesson. I'm going to go through it real quick. This is the theory part about it on the right hand side. And on the left hand side is the practical example, mathematical example. I'm going to go through the theoretical part real quick and then we can start going through the example. And from there on, we're going to move and see how this is applied. So to be quick and fair, we're gonna have number of population that represents the amount of wolves in the pack. So we're gonna have three most dominant wolves that are gonna be leading the answer, that are gonna always have other wolves following their direction to be able to reach the answer. The most dominant one is the alpha wolf, the second dominant is the beta, and the third is the delta. The remaining wolves, whatever the amount is, are all packed in a group called omega wolves. So we're gonna follow the steps that I have mentioned. We're gonna be searching for the prey, encircling the prey, hunting for the prey, and attacking the prey. When we are searching, we're exploring different places in the space. When we are attacking the prey, then we already know its location. It is within our space, and we are just going to exploit to get to the answer. So, moving down here, we can see that there is a value A that is going to be changing throughout the iterations. And the value of A is what makes us special about the wolf optimization, gray wolf optimization method, because when A is more than 1, then we are looking outside the space, we are exploring the space. But when A is less than 1, then we are looking within the prey, within the solution, within the space. This keeps a good balance between both exploration and exploitation. As we can see here, when A is more than 1, it's looking outside the circle. When A is less than 1, it's looking within that circle that eventually is going to reach the prey. Moving on to further part of one of the papers, we're going to see that the omega wolves are always following alpha, beta, and delta wolves. And by following them, they're always getting closer and closer to the prey. As we can see here as well, we have linear algorithm steps. You can see that omega is always following alpha, beta, and gamma. Here you go. And at the end, it is always next to it, close to it. So it is moving on to getting the right answer to converge. So we have an equation that we need to minimize. The equation is f of x, which is equal to y. It's going to be just whatever random equation we need to choose. We chose 2.4 to 27x1 plus 7.135x2. So coming into the question, we need to minimize that equation. To minimize the equation, we need the best solution for that equation will give us the lowest value, the lower value. That would be the minimal value. So we have a population in the example of n equal to 4, and will tell us how many random solutions we are generating per iteration. The number of iterations is 100, as you can see here. We have to find x alpha, x beta, x gamma. They're all gamma and delta are just the same used words for the third best dominating wolf. They're sometimes called gamma, they're sometimes called delta, but they are referring to the same third most dominating wolf. For each iteration, we're going to find the value of a. Then we're going to find a value for x1, x2, x3. Then we're going to find the new answer for x. The new answer will be the mean value of all three x's. And then the limitations of our answer in terms of y1, y2 will be similar to the same limitations that we have in the question for x1 and x2. We're going to pick a greedy selection that gives us the minimal value. That is going to be the minimal value that we get for f of x. So moving on to step number 2. These are the equations we need to use to find x1, x2, and x3. This is the equation we need to use to find the new x, which will be the mean value, adding them all up, dividing it by 3. To find a, we're going to be using that formula, that equation. The random variable that is going to be used inside these equations will be a value between 0 and 1, randomly generated by your algorithm. So we are moving here. We're trying to minimize that function. We're going to have to get random variables, and as the population is 4, we're getting 4 random variables. This is the first random one, second random one, third, and fourth. So we got, since the equation has to have x1 and x2, so for each population n equals 1, n equals 2, n equals 3, and n equals to 4, we're going to have two values, one for x1, the other one will be for x2. So n1 contains a random x1, random x2, n2 contains another random x1, another random x2, so on and so forth. So we got the table right here with the generated values. We will be the ones who are going to determine the x-wolves, the alpha, beta, and gamma. How are we going to decide which wolf is which? We're going to go and find the best solution that we have in our current variable, in current data. What value makes us have the minimal value for the function? We're going to replace x1 and x2 in the equation here for the values, and then see what we get for fx as a solution. Then we're going to choose the best solution will be the minimal value of fx. In our case, if we check out these values here, the minimal one is 2.1, which will give us the value for alpha wolf. Second minimum is going to be the beta wolf, which corresponds to an answer of 2.95. Over here we gave that value corresponding x1 and x2 values to beta. And for gamma, for omega, we don't have to look for omega. For gamma or delta, we're going to choose the third best value. In this case is 3.12, and we're going to give it to the gamma wolf. So once we choose these values here, we put the corresponding x values, and they're going to be responsible for x alpha, x beta, x gamma for the remaining part of the question. X of t will move from the first value to the second value to the third to the fourth. So xt will start as 0.54, 0.23. That's the first row. In the next comparison, it's going to be the next values of x1 and x2, which it will be x of the second row, and then the x's will be for x of the third row and the fourth row. And all these are going to be done within the first iteration. So moving on to the new continued part of the question, we have to find the values for x1. To find the values for x1, we need to replace the values with the given ones in the equation. It's always 2 times 1 minus the iteration we are in, which is the first iteration, over the number of total iterations that will be done, which is 100. So it's 2 times 1 minus 1 over 100 is going to be 1.98. This is the value for A. Value of A is always constant here and here. As we can see, it's always kept constant as 1.98. At each iteration, it's constant. Next iteration is going to be 2 over 100. It's going to give us a different value. We're going to get a random variable that's going to be 2 times that's A times the random variable, which is going to be 0.54 in our case, that we just any number between 0 and 1. And then for B1, we did similar calculations, 2 times the random variable, 1.08. And I'm giving you a notice that the random variable is always changing within the calculations. It's just a coincidence that we got 0.54 for both random variables, but in general we can just replace it by any other variable at each step of calculation because it's total random, right? For C alpha, we're gonna multiply B1, the value that we got here, which is 1.08. As you can see, multiply by X alpha. X alpha consists of X1 and X2. So we're going to have to replace one value for X1, one value for X2. This is why we have two equations. Or we can multiply by X alpha as a form of a matrix and then put the value of X1 here and X2 here. And then our answer C alpha will be also a form of matrix, which will give us a value here and a value here. So we got values of 0.17172, 0.03668. And then to calculate x1, we need to subtract a1 times c alpha from x alpha. This is what we have done here exactly. We got the answer for x alpha as the values that corresponds to the best solution. We are replacing them here for x1, for x2 down here. This is for the first answer that we got, 0.17 will be here. Second answer is going to be for x2, so it's going to be down here below. Instead of writing a lot of equations, I would prefer to do it as in a matrix form. Just replace it by the matrix so you can get a direct solution. X1 is going to be the answer for x1. It's going to consist of small x1, small x2, because each answer, or let's say candidate solution, will be consisting of two x's to be replaced in that let's call it a cost function f of x. Moving on to the next part, we need to find the answer for x2. Similarly, we're going through the same calculations. As we can see, a is not changing for the same iteration. For a random variable, it's 0.33 here, it's 0.71 here. So we are changing the random variables continuously in all the calculations. Replacing x beta values over here, we can see that x1 of x beta is 0.54 and 0.23 for x2 of x of beta. Then we're getting the final solution for x2 here. x2 capital is giving us a value for x1 candidate solution and small x2 as a candidate solution. Going to x3, we're gonna do similar calculations. As we can see, the random variables are again changed to a different values here. Once we get all the x1, x2, x3s calculated here, we are having these three values for x1, and these three values are gonna be for x2. I'm not gonna overwrite it because it's getting ugly, but these values in the first section are for x1s, second section is for x2s. So for the new x, it is gonna be x1 plus x2 plus x3 divided by 3, the mean value of them all. To find it, we need to get the x1s here inside this equation here, divided by 3 to get the final answer here, 0.3951, which is the average value for x1. The second average is going to be the sum of the x2s all together divided by 3. It's going to give us 0.169996. That is the x2 value. So once we get the x1, the x2, this is going to be the component of the x1 for the new x value, which will be written here. Second one will be written here. As we know, a candidate solution should consist of both x1 and x2s. We've got x1 and x2 written in here. As we can see, the new values will be substituted in the equation, this equation, the one we started with at first. Once we replace x1 with the new value, x2 with the new value here, we're going to find that the answer was 2.17377. And when we find this value here, we're going to compare this value with the x of t. What was our choice of x of t? X of t was this first solution up here. This was x of t here, 2.95163. So when we come to comparison, when we come to comparing them both, we find that our new solution is smaller than the old solution. Therefore, we are eligible to change the values and put x1 and x2 as the new values we found here, in here, and then writing the minimum value of 2.17 in the place of the first x of t. X of t will now change to become the second value here, second row values, and then the same iteration will be repeated for x of t's until x of t reaches the last value. And once you reach here at the end for x of t and perform the same calculation we did for the fourth one as well, we're going to jump from that first iteration to the second iteration. We're going to start over and over and over. I'm going to explain to you real quick what changes happen between each x of t changing. So when we found that this value is 2.17, we found that our x alpha, we have to choose our x alpha, x beta, x gamma from the start. So smaller value of the function will be this. So the corresponding values of x1 and x2 will be the corresponding value to that gives us this total of 2.104. The second biggest is now this value, new value we got here. So x1 and x2 for x beta or beta is going to be the new values that we obtained in the last calculation. And gamma will always it's not always, it's like the third let's say third least value, which is 3.123983, which is equivalent to these x1 and x2s. Once we know that these are the new values for x1, x2, x3, x alpha, x beta, x gamma, we found their values, the corresponding values of their x1s and x2s. We are getting the x of t as the second row values, like we can see in here, which are these values here, which is 0.341 and 0.179. Once we get that as x of t, we're going to use this new x of t, we're going to use the new values of the wolves, and we're going to replace them in the equations before. We will get the new values of x1, x2, x3 like we did in the last calculation. We're going to get a new x, which is the main value for x's added up together. Then when we calculate the values for x1, we're just going to add up the x1s together divided by 3 to get this answer here. To get the x2 values, we will add these all up in here, divided by 3 to get this value here. Once we get that new x value for x1 and x2, we're going to substitute them in the original equation, check out the final answer. Then we're going to start comparing it with the corresponding value of xt2, the second t, which is this number right here, 2.104. So when we come down here, we are comparing the value with 2.104, and then if 2.104 is greater than this value we found here, this shouldn't be that, this value should be 2.104. If it's less than that, then we're going to substitute the x's. If not, then we will keep the value as is, and it's going to be 2.104. Then we're going to move on to xt as the third row, continue our calculations from there. Since it is not less than this value here, so we are not going to change the x values for it. We're going to continue by iterating even further to find out the total and true answer for it. After the 100th iteration, we will find out that the solution is not changing as much because the answer have been converged eventually. And this is where we stop doing our iteration, and this is where we get our final answer. We can converge within 10 iterations, 20, 30. Depends on the question, depends on the values, variables you have. You can have x1s, x2s, x3s, all the way to 100, 200. Depends on your question. It's a really flexible method. It's going to work with all variables, all different kind of x's. And this is the cool part about it. I hope I could explain briefly about this method and solve an example about it. If you have any questions, please let me know down in the comment section below. And thank you all for your listening and understanding. I will see you soon.